welcome to Microservices Lesson Learned from a startup perspective. And when we usually talk about microservices, we hear and read a lot about success stories from large industry players such as Netflix, Amazon, eBay, just to name a few. And when you look at those success stories, especially from a startup perspective with far less resources and far less experience in a large scaling world, you might end up saying, well, that's fantastic, just let's copy that. But the problem is that every journey is different. So what works in one company might not work for you. And so unfortunately is that there is no golden, easy rule that's easily applicable. And each journey is different because every company has to face different circumstances. So, and one of those circumstances could be, for example, your team, your legacy system, and also your strategy. So microservices come with a lot of complexities, which requires different skills, different tools, and a cultural shift towards a DevOps culture as well. So, and your team size and skill set and also your structure has a huge impact on what is manageable for you. Especially when you start with a small team with less DevOps practices in place, it will have a huge impact on your velocity of your transformation process. And especially if you have to take care of a legacy system, so it's not going aside, it's still there that you have to maintain. And the more maintenance effort you have to put in your legacy system, the less time is available for your transformation process. And also the environment itself is impacting your journey as well. For example, if you're running on an on-premise environment or on cloud native, where all your services are managed, for example, a managed API service, or on an on-prem environment where you have to set up everything and maintain everything and operate everything. And if your strategy is to implement new features in a very short period of time, because you have to match some timelines and also some milestones, you're really challenged in how to implement these new requirements. So do these new requirements go back to the monolith again because you have to meet timelines? Or can I add new services and I have a little bit more time? To give you a background, so I am the former CTO of Just Software, and that's a startup in Hamburg. And at Just Software, we're developing Just Social. Just Social is a collaboration tool that provides a digital workplace for communicating, collaborating in teams. So, oh, this is not working, I'm sorry. And to give you a background, so we started in 2010 with a monolith in every aspect. So we had one team working on one collaboration product, which was based on one code base, based on one technology stack. And after a while, everything got bigger. So we're adding more features to our product itself. Our team was growing, and also new users increased, came into the play. And this usually seems to be very, very great. But on the other side, everything got kind of clunky because everything was tied together. So, for example, from the organizational perspective, our meetings and decisions and discussions took longer than original. And also adding new features constantly to our product was affecting that our user experience and user interface of our product was suffering. So instead of solving our customers' problem very easily, we were confusing them. On the other side, also on our software architecture itself, it was still a monolith, and it was very hard, very complicated to add new features without impacting the entire system, and it was not easy to release new changes very soon, because we have to rebuild and redeploy everything, even though if we just add or modify one single line of code. So new features release very slowly. And there developed a kind of need to shift and split things. So 3 years ago, we changed our product vision, our product strategy, and we had the idea to split our one collaboration product into separate collaboration apps, and each of them is taking care of a specific use case. So we had we developed the idea to have a separate app for communicating in real time, for managing your tasks, for sharing your documents, for managing your users, and also for enterprise social network. In the meantime, we also split our one team into smaller, separate teams, multiple teams, with a focus or with the goal to establish small autonomous teams with well-defined responsibilities. And we assigned to each of them a specific set of collaboration apps so that they can work at different parts of the system independently at their own speed without an impact across all the teams. So after we have split our one product into separate collaboration apps, after we have split our one team into a smaller one with well-defined responsibilities, the need, so it was a kind of logical next step to also split our software architecture into microservices. So we started with the idea of a straightforward process where you have your starting point as your monolith and going straight to the end where your monolith is 100% decomposed into microservices. So yeah, this was kind of like theory because reality gave you a really brutal lesson, and this one is that the journey to microservices is a way with a lot of detours and also failure, and it might never end. So the first approach that we did, that we extracted one of our collaboration apps, which is taking care of document management as a coexisting service and developed it from scratch. But it was not an exact equivalent. Instead, we also added a new user interface, and we added new features as well, and also introduced a totally different data structure. This document management that's called Just Drive is having the data authority over documents, so it's the only one that can modify the documents. And each document itself is created by an author, and an author is stemming from the profile data, which is still residing in the monolith itself. So to avoid requesting the profile service each time when we are displaying a document, we kept a local copy inside the document service. So that we are independent from a request-driven call on the document service to the profile service or to the monolith at that time. So, but whenever a profile itself got updated by the monolith, it has to notify our document service so that we can then update the local copy itself accordingly. So the problem was, the lesson that we learned was that we took too many steps at once, and that slowed us down. So there's nothing wrong with creating a coexisting service from scratch, but the problem is that we involve too many other steps as well. So we also introduced a new user interface, a new data structure, and also added more features than the original equivalent. And in the meantime, we also had to maintain and run our current systems, and we have to match also, and we have to meet also timelines. So the thing was that the time that we originally anticipated was not, we could not meet that milestone at all. So it took far longer than we originally anticipated, and it was frustrating because we could not get a very easy release, a very soon release. So what we did instead with the next one was that we started, the next one was manageable step and one at a time. And so the next one was that we used those ones that are easier to extract, that has less dependencies in the monolith. So this accelerates your extraction process, and it gives you the ability to gain experiences with microservices, but also with the extraction process in particular as well. And the next one is also focusing on those services that gives you the greatest benefit after you have extracted those. And this could be, for example, potential candidates that are changing frequently. So after you have extracted those one as a new service, you can release the new changes very easily and very quickly. Or you can also identify next candidates as those ones that are using different resources. For example, if you have a service that needs a lot of CPU power, you can then, or memory consumption, then you can extract those services next. And after the extraction, you can deploy it on a different machine with different power and can scale it more easily. And another approach that we did is we even cut the decomposition process in smaller steps. So it was kind of like incremental process. And we split it in the decomposition process in steps and with an incremental approach in terms of that we went top to down. So we extracted the user interface first, then we extracted the business logic, and afterwards the data storage. And then we had a full extracted microservice at that time. Another problem is that we have not solved security in terms of authorization early on from the very beginning. And postponing handling authorization is very counterproductive. Because with every new service that you would like to implement, you are confronted with the question how to handle authorization. And if it's not solved at that time, there are two counterproductive consequences. You either put the new service into the location where authorization is still solved, and this is your monolith. And if you put it in the monolith, your monolith grows instead of shrinks. And you're feeding your monolith again. And the other one is that what happened as a consequence as well is that some teams started to re-implement authorization with every service. And to give you a little context about our authorization is really, really fine-grained. So, for example, you can modify or you can adjust the authorization down to object level. So if you, for example, would like to upload a document, you have to have the permission to upload it to a specific share. So your share is controlling the authorization of your document. The other thing is that also our authorization is inter-service dependent or inter-app dependent. So for example, if you would like to upload a document within a content page, this authorization is then controlled by the page application. So, and the document itself is sitting on a different service. So you have also inter-service related authorization. And what happened when we implemented the authorization on service level, it's not only that we were duplicating code and re-implementing the same business logic again and again, but also we had to copy data back and forth because the services were interdependent. And this is the thing is that authorization is a cross-cutting concern which has to be implemented in our case as a central service. And so solve your authorization handling or your cross-cutting concern relating to authentication authorization early. It must be the first step, that's my opinion, in your microservices journey. Otherwise you end up making some detours that will be very painful because, for example, if you try to merge the services that you have implemented on service level, it's very, very expensive. And what's also very expensive is a less aligned strategy. So we split our product into separate collaboration apps, and we had separate teams working as autonomous teams with well-defined responsibilities, and we also established separate services, and they all had their own artifact because assigning its own CI and CD pipeline. But the problem is that we bundled them together again at the deployment, and there was a kind of like strategy shift sneaked in because we are running our solution also on-prem environment, and the customer installation on customer prem environment increased. So, and the customer themselves, they requested not a deployment per service, but instead they all wanted to have a bundled deployment. And so the problem is that we added a lot of cost to separating everything, but in the end we were deploying it in one bundle. And this is something that you can't really benefit from your microservices in its full extent if you then just deploy it all together again. Instead, you should be able to release one service independently. So it's really important that you have to look at your strategy and to figure out what slows you down and what holds you back in your microservices journey, and try to adjust your strategy as well. The next point is that with every stateful service that manages its own data comes with overhead. And so you have, for every service, you have to set up a data storage, and you have to maintain it. And in case of that, you keep a local copy of data in your microservice that relates to other service. You also have to take care of it, that you have to keep it in sync. And this adds a lot of overhead to your introduction of new services if you have to do so many steps. And so what we introduced then recently, that we try to lower the barrier of entry for new services with Apache Kafka Streams. So who of you have heard of Apache Kafka Streams before? Great, and that's probably one quarter. And who of you is running Apache Kafka Streams in production? Okay, that's a few, okay. So, before I go into Apache Kafka Streams, I go a little bit back to the interaction communication styles of services. So, usually when you introduce or when you establish microservices, you have to make sure, or you have to take care how the services are interacting with each other. And there are different communication styles. So you can follow the request-driven approach, where each service is calling another service directly over its API, in a command style where you expect an action be executed on the receiving end, or as a query where you retrieve information. And so this gives the sender of the request the control over the request flow in case you are dealing with a synchronous communication process. But on the other hand, it also increases the coupling between the services, because services are very tied together. In the event-driven communication style, you are instead communicating via events. And so on the one side, you are submitting events to your event stream, and on the other side, consumers are consuming these events and act independently based on these events. So, the request flow, or the logic itself, it's flipped. It's now not the sender that controls the request flow. It's now flipped to the receiver, who takes control over the request flow itself. And so we achieve higher decoupling between those services, and autonomy, and also pluggability. And you can also, the question arises also, shall we run with a hybrid model where you combine those both patterns, event-driven and also request-driven? And another question that arises when introducing microservices is also how to manage data. So in a hybrid model, you're combining the event-driven and the request-driven approach, as I mentioned earlier. And so in this case, you are listening to events, but if you are depending on some information from another service, you are doing request-driven remote query directly to your source. So in this case, the event stream is purely used for notification, and additional data is requested directly. So as I mentioned before, the request-driven approach is tying your services, coupling your services tied it together. So it's still kind of like high coupling between those services. Another approach is then that I have demonstrated when we extracted our document service as a coexisting service from scratch, is that you keep a local copy, because one of the approach that in the hybrid model is that you try to avoid the remote request, the remote query to your service itself. And you can internalize your request by keeping or creating a local copy of the data that you need from the other services. So in our example with the document service, we're holding a copy of the profile, but only which is related to the author data, like first name and last name ID, and not for example not the address, because this does not matter in our document service. And this one is giving you better decoupling between those services, because you are not querying the other service as a remote call. And on the other side, it also increases your autonomy, because now the document service itself can now do with the local copy whatever it likes to do. And also the joins are now more efficient, because the joins are now handled locally instead of over the network. So in this case, the events are not only used for notification, but also for transferring the state. Because whenever, for example, the profile service has a profile change, a profile update, it sends a message to the message stream, and the document service is updating the local copy of the author data, which is stemming from the profile accordingly. So you're transferring state from the profile service to the document service. And another aspect of when you that is data related is the source of truth. In a traditional event-driven system, you are listening to events and you are saving its actions in a database, in a local database, and you are raising new events as well. So the thing is, what has to be considered in this traditional event-driven system, that you have to deal with multiple sources of truth, because for your service that has its internal database, the database itself is its internal source of truth. But for all other services, for all other services, it's the event that are their source of truth. And this comes with issues, because you're doing a dual write on the database and also for triggering an event. And so you have to take care of making these transactions consistent. And on the other side, the data model of the database and also the data in the events can diverge over the time. So that you, for example, then you're consuming services have to deal with another data model than, for example, the data model in your database. So an alternative to this is to merge those both into one store, and to make your events as first-class citizens that can be used as a data store itself. An event can then be represented as a whole fact, which is then representing a data record in its entirety, or also as a delta that you, for example, just add the delta action, and you then can derive the state from the delta of the event as well. And here comes Kafka into play. That is very good at storing events, because it's keeping events backed to disk, and it's a distributed, fault-tolerant, scalable commit log, which was originally created by LinkedIn and is now open source. And so, how does it work? So in Kafka, you have a producer. That could be one of your services, for example, our profile service. And this writes records to a topic. A topic itself, it's kind of like logical category or feed name, for example. And a topic itself, it's consisting of one or more petitions. A petition itself, it's an immutable ordered sequence of records that the producer writes writes its messages to, its records to. And so whenever a producer writes a message to the topic, it appends the message, the entry itself, to the end of the partition. And the producer also controls into which partition he writes his record. And this could be a round-robin mechanism, but also a kind of like semantic partition function. For example, the profile ID, the ID of the message itself. And on the other hand, we have the consumers that are consuming those messages from the topic they subscribe to. And the partition itself is that each partition itself is assigned to only one consumer in the consumer group, and so that you have a partition exclusive consumer on the one side. And the effect of this is that you have a load balancing between the consumer instances of a consumer group. So I forgot to mention that each consumer is related to a consumer group. So whenever you have your service, for example, and you're running different service instances, so the service instance is a consumer and it relates to your service as a consumer group. So, and because we have each partition is assigned to exactly one consumer instant within the group, what we achieve by this is that each message is load balanced between the consumer instance of your consumer group and also broadcasted to each consumer group. And on the other side also, which is very elegant, handled by Kafka, is that each consumer can control its position per partition. It's called offset. So this guarantees that Apache itself is scalable, fault tolerant, and very fast. So the topic itself, for example, can also be scaled out to several nodes. So it might be the case that one topic does not fit in one server node. And you can add separate server nodes itself. And then on the other side, the messages are also load balanced, as I've mentioned before, which is then increasing the scalability. And you can also add more partitions to your topic, and this also is then increasing your parallelism of your system, of your service. And you can add capacity with zero downtime. The fault tolerance itself, it's created by the fact that the data is stored to disk. And the partition itself, if you have more than one node running, are replicated. So that your nodes itself can, for example, shut down and it's still running. And also that the consumer is controlling its offset has the effect if one consumer instance goes down and the controller controls its offset and committing it to the Kafka controller, where the last position he was reading from the topic itself or from the partition. So, for example, when one consumer goes down, the Kafka controller can rebalance then the partitions to the remaining consumers, which is really, really good for fault tolerance. And it's also very fast. I only have a number from 2016. So LinkedIn was processing 1.4 trillion messages a day about over 1,400 brokers. So yeah, it's very fast. And what Kafka combines is, it combines a messaging system, a storage system, and also a streaming platform. So as a messaging system, it provides, on the one side, a queuing mechanism, because each message goes to exactly one consumer instance in a consumer group, and also publish subscribe mechanism, because each message is broadcasted to every consumer group. It also provides a very good storage system because data is stored on disk, and it's also fault tolerant and very scalable. And also provides a streaming platform where you can process an input stream, process on an input stream and generate an output stream. So I'm now focusing on the streaming platform. So as I said, there's possibility, two possibilities in the streaming platform. That's on the one side is stream processing, but also data integration. And with stream processing, you are you're generating a stream of input data that's continuously updating, and you perform some action on this stream and generate also then an output stream on this. You can use it also as a data integration, and you can integrate, for example, a relational database and also as a source, and also, for example, Elasticsearch as a sink. So, for example, that you are on the sink side, for example, that you capture your events and streaming them, to transform it into a stream and connect it then, for example, to Elasticsearch. And on the other side also you can integrate a relational database. So whenever you do, because a relational database is containing a transaction log as well. And so whenever whenever your database, your external database gets updated, the stream can then feed those updates into your message system as well. So it can integrate external data system either as a source as also as a sink. So what is a stream itself? So a stream itself is an unbounded ordered sequence of data records that they have a well-defined structure. It's representing a key values pair, and this stream is continuously updating. In Kafka itself, it's the topic that can be loaded into a stream. So Kafka itself provides a stream API, and the stream API provides a domain-specific language that lets you joining streams or filter them or group them or aggregate them. And the essential part here is that the stream API is running on your code in your microservice, and it's not running on the broker. So this means the streaming processing itself is running in the process of your microservice. And at startup, when you start up your service itself, when you created a stream out of a topic, for example, this topic gets loaded into the stream at startup time and then processed continuously. And the topics themselves or the streams themselves are buffered in Kafka within state store. That's a lightweight embedded database. It's RocksDB. That's a key value pair database store. And you can also create your own state store as well. I'll come to this one in the next slide. But what's really, really important here is that your streams now are made available wherever you need it, and it's located in your own microservice. It's not running on an external system. And this also lets us using Kafka streams for materialized views. So as I mentioned before, when we had the usual setup of a microservice, stateful microservice, we had to set up a database and keeping a local copy for all the data that's sitting in another service. And this we don't have to do anymore. So instead what we do is we create a stream in our service itself. For example, from the document topic. So when I would like to display a document itself, I create a stream from the document topic, and I would like to enrich it with the author data. This is residing or stemming from the profile service and stemming from the profile topic. And what I do is I create a table from the profile topic for enriching my data from the stream itself. And those stream and those table I can join together, and as a result I can create another state store in my own service. And this is all running in my service itself. And this state store that I have created as a result from joining my stream and my topic, my table, can be used as from outside. So I can access it. I can place an API on top of it and then requesting the information from this data. And the good thing about this is that you don't have to take care anymore updating your local copy. So it's just coming automatically that your document data along with its author data is automatically updated. So what Kafka streams provide is, especially for materialized view, that it's lower the barrier to entry for your new service. So you don't have to set up a separate data storage anymore, and you don't have to provide or establish local copies or caches to set up and to keep in sync. And you don't have a remote call to the other servers and increasing now decoupling. And your materialized view itself, it's always up to date, and it comes with a scalable and fault-tolerant and fast data storage that Kafka provides for you. So it's reducing the overhead and that you have usually when you have to manage data, and it's increasing your performance and also your autonomy, because each service can now run on its own streams and can generate its own materialized view, and it's all updated from Kafka, and you don't have to take care of synchronizing anything anymore. So if we could start the journey again, what would we do differently? And as I said in the beginning, yeah, we would start with one step at a time and also adjust this step to your size that you can manage. Don't take a pill that's too big to swallow. And so start with manageable steps and try to start with small services where you can achieve a very fast experience with microservices and also with the extraction process of microservices. And also take care of your cross-cutting concerns that are, for example, authentication, authorization. In our case, it was authorization. And take care of those one very early, because whenever you introduce a new service and these cross-cutting concerns are not solved at that moment, you are generating some very, very strange impacts or very counterproductive results in terms of that you're feeding the monoliths again, or that you are re-implementing logic, or re-implementing something which has to be kept together as one separate central service itself. And also, if you figure out that something is slowing you down or holding you back, in our case it was that we were bundling our artifacts always together as one deployment, as one bundle deployment, then it's a time to readjust